সকলে?
Yes,
Yes,
ma'am.
ma'am. Yes, ma'am.
Okay, so everyone, please write this topic. Today's topic name is Boolean algebra and digital logic. Have you finished the last topic?
Yes, ma'am.
আমরা লাস্ট টপিক কি পড়েছিলাম?
Uh,
Last chapter. What was our last topic?
Ma'am, number system.
Number system and code.
Yes, ma'am.
constant r minus s constant টা পর্যন্ত পড়া হয়েছিল, এরপর আর পড়া হয় না।
We did not
আর একটা
see
বাকি
that.
আছে।
Yes. Okay, so later we will see. So today we will start this one. So see the objective, understanding the relationship. The objective is understanding the relationship between the Boolean logic and digital computer circuits. Learn how to design simple logic circuits. Understand how digital circuits work together to form complex computer systems. So these are the targets for this chapter. In the latter part of the 19th century, George Boolean, actually we just now we will discuss something from where the Boolean algebra is come. So the scientist name is George Boolean. Engaged a philosophers and mathematicians alike when he suggested that logical thought could be represented through the mathematical equation. That means at first they have proposed that yes, whatever the logical thinking we do, that can be proved or that can be represented through the mathematical equations. Okay, so their dialogue was this one: how dare anyone suggest that human thought could be encapsulated and manipulated like an algebraic formula. The question was, the research question was this one, that how for everyone's mind was that how that can be represent our human thinking how can be represented at algebraic form, is not it? So if I say that your think I can represent in the mathematical formula, so obviously the question will be in your mind that how we can do this one, is not it? So the computer as we know them today are implementation of Boolean's law of thought. John Atterson and Carl Spano were among the first to see this connection. So now we are reading the history, basically the history from where the Boolean algebra is come. In the middle of the 20th century, computers were commonly known as the thinking machine and the electronic brains. So another name of computer is thinking machine and the electronic brain. Okay, so many people were fearful of them. Those who does not know, they were very feared of the computer, that how it can be a brain, how it can think, how it can give us output. So nowadays we really wonder the relationship between the electronic digital computers and the human logic. The computers are accepted as part of our life. So many people, however, are still fearful of them. In this chapter, you will learn the simplicity that constitutes the C. So did you understand the philosophy behind the Boolean algebra and the computer? These are the philosophy. Actually, behind every invention, there have a philosophy. Okay. So Boolean algebra is a mathematical system for the. So now we will learn what is Boolean algebra. Boolean algebra is the mathematical system for the manipulations of variables that can have on or two values. Okay, on or two values. So this is the definition of Boolean algebra. You will say in formal logic these values are true and false. true and false. That means this is obviously a mathematical representation, but in formal this value will be true or false. So if I ask you the definition of Boolean algebra, so you have to see this one and you have to be prepared for the Viva question. From this slide we got the Viva questions also. Okay, so in digital systems, these values are on and off, and 1 and 0 or high or low. We can say on off or 1 and 0 or high or low. Okay, in digital system. So Boolean expressions are created by the performing operations on Boolean variables. Common Boolean operators include and, or, and not. So these are the common Boolean operators. Also we know these are the basic logic gates: AND gate, OR gate, and NOT gate. So can you hear me or did you understand?
Yes, ma'am.
I got it.
One is responding. Okay, so from now we will go rapidly. Okay, otherwise we cannot finish it, so you have to concentrate. So see, Boolean algebra. So now see, there have a truth table. You're familiar with this one. So we are denoting two terminals for input. One is X, another terminal is Y. You can denote this is as A, B, C, D, anything. Okay. So a Boolean operator can be completely described using a truth table. So if I ask you that how Boolean operator can be described, so you have to say the answer is the Boolean operator can be described using a truth table. Or if I ask you that why the truth table is needed, why we use the truth table, so the answer will be that we use the truth table to describe the Boolean operator. Okay, so the truth table for the Boolean operator and or are shown in the right. The AND operator is also known as a Boolean product. Okay, so here also one question you got on important information, that AND operator is known as Boolean product. Okay, so the OR operator is the Boolean sum. Okay, so Boolean sum is OR operator and Boolean product is AND operator. So if you want, you see the truth table and a word. Now the truth table for the Boolean NOT operator is shown as the right. This is the NOT, that means opposite. The NOT operator is most often designated by an over bar. So this is called bar, over bar. Over bar means this will be in upper side, over bar. Okay, it is sometimes indicated by a prime mark. This is called a prime mark. So that can be indicated by this one, also by this one. Okay, or an elbow. This sign is called an elbow. So you can indicate the NOT operator in three ways. So by a over bar, by an elbow, or prime mark. This is a prime mark. Okay. So a Boolean function has three features: at least one Boolean variable, at least one Boolean operator, and at least one input from the set 0 and 1. Okay, so these are the features, these are the functions, Boolean functions features the Boolean functions has. It produces an output that is also a member of the set 0 and 1. So it will take an input from the member of the set 0 and 1. Also the output will be 0 and 1. Now the thinking is how with 0 and 1, only with these two digits, the Boolean algebra can express the human thinking. Is not it? That was the question. So now you know that why the binary numbering system is so handy in digital systems. So now have you understand that why I revised previously that the binary system and binary conversion, every binary conversion, why I taught you? Because now you have to need for every step. Okay, now observe the truth table for the Boolean function. So Boolean function is f. The function is denoted by f. From the early childhood math, we are learning this one. That function is denoted by f. So inside f, these are the components. This is x, y, z. So the function x, y, z is equal to x z bar plus y. This is the Boolean function. Now express this as a truth table. So already we did this kind of things in our 103 earlier courses. Okay, CSC 103. So just now you revise how this is. So x z bar means we have to do the not of the z value. Then we have to perform here the AND operation with the not z value with x value. Okay, x z bar, that means x and z bar. Okay, plus y, that means with this value y will be OR operation. Plus means OR operation, so multiplication means AND operation. So at first we will give 3 input. So if we take 3 variables, so how many combination will be there for unique input? 2 to the power 3 equal to how many combination? 8 combination. If there is 2 input, how many combination? 4 unique combination. If there is 4 input, how many unique combination will be there? 16. Okay.
Yes,
Obviously, previously we did all these things. So see the truth table. What is the output we are getting from the truth table? X, Y, Z. Then we find out Z bar. Then we find out X and Z bar. So did you understand this truth table? X and Z bar means X and Z bar. We have to perform the AND operation with Z bar and X. After that, you have to with this result, you have to do OR operation of Y and this result. So 0 or 0 0, 0 or 0 0, 1 or 0 1, 1 or 0 1, 0 or 1 1, 0 or 0 0, 1 and 1 is 1, 1 or 0 is 1. Okay, so this is the final result. So to make evaluation of the Boolean function easier, the truth table contains extra shaded columns to hold the evaluation of the subparts of the function. So as with common arithmetic, Boolean operations have rules of precedence. So you have to follow the rules of precedence. Rules of precedence is at first you have to do the NOT operation work. The NOT operation has the highest priority. You have to remember which the precedency of the operator. So NOT has the highest priority, followed by and then what? So at first the highest priority is NOT, then priority is and, then the priority is what? Okay, clear everyone? So this is the priority of the Boolean operations. This is how we choose the shaded functions as parts in our table. Now, digital computers contain circuits that implement Boolean functions. The simpler that we can make a Boolean function, the smaller the circuit that will result. The simpler circuits are cheaper to build, consume less power and run faster than the complex circuit. With this in mind, we always want to reduce our Boolean functions to their simplest form. There are a number of Boolean identities that help us to do this. Okay, now most Boolean identities have and means product. Now we will learn the Boolean identities. Okay, so most Boolean identities have and means product form as well as or means some form. So they have and form and or form. Or form means sum and form means product. We give our identities using both forms. Our first group is rather intuitive. So let's see the identity name. So our first identity law, null law. Then this is the identity law, null law, idempotent law and inverse law. They have 4 law identity. Okay, so let's see identity law. What is identity law in and form? In and form, everyone please observe. You have to remember this law. These laws are very important. Okay, so now we are reading the identity law for and form. What is the and form identity law? Is that 1x is equal to output will be x. That means 1, if with the 1, if you do the AND operation of any other, so that will be, the value will be x. This is for identity law in AND form. Okay, then or form will be 0 plus x is equal to x. You have to remember all these things. Okay, then null law is 0 multiplication x is equal to 0 for AND form, 1 plus x is equal to 1 for OR form. Okay, then idempotent law. Okay, so this will be x multiplication x is equal to x. This will be in AND form, x plus s. These are the equations law. Okay, so you cannot change it. These are the laws, so you have to remember it. Okay, so x plus x is equal to x. So this will be idempotent law. Then inverse law. In inverse, x multiplication x bar is equal to 0 in AND form, and in OR form x plus x bar is equal to 1. You have to remember all these things for the logic design. Okay, so this table is very important. Now inside the identity and others law are also there. Our second group of Boolean identities should familiar to you from your study of algebra. So this is commutative law, associative law and distributive law. So these 3 are the most important law for this chapter. So we will learn the commutative law. Commutative law is x multiplication y bar is equal to y bar x. This is AND form. Okay, so x plus y bar is equal to y bar plus x. Then associative law. In associative law, so there have brackets x y bar multiplication z. So the AND form will be x multiplication by y bar z bracket. Okay, then The or form will be for associative law x plus y plus z equal to x plus bracket y bar plus z. Okay. Then this distributive law is x plus yz is equal to in bracket x plus y in bracket x plus z. X multiplication y plus z is equal to xy plus xz. Okay, so you have to remember this law and equations as well as the next slide. Our last group of Boolean identities are perhaps the most useful if you have studied set theory of formal logic. These laws are also familiar to you. So the identity name is absorption law. Yes, what happened? Lots of net problems. Social number 13. Okay, so no problem, but you are missing the classes. That is the identical thing. Okay. So absorption law is x multiplication in first bracket x plus y is equal to x. So x plus xy is equal to x. Now De Morgan's law. This will be very helpful. That De Morgan's law, this one. Okay. So the De Morgan's law is that x y bar is equal to x bar plus y bar. X plus y bar is equal to x bar multiplication y bar. Double complement law. So you have to remember De Morgan's law and absorption law. So double complement law is x bar over bar is equal to x. That means if there have double bar, so that will be the normal one, normal x. So these are the law. You have to remember the law form for or and form. Okay, so clear everyone. Now see, we can use Boolean identities to simplify the function. So till now we have read the law. Now using that law we will simplify the function. So everyone please copy this math. Everyone. Are you listening to me?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
So these are very important and also critical if you don't concentrate. So see the function. Function is f of x, y, z is equal to x plus y bar. So function is this one. So x z bar. Okay. So now see the idempotent law is rewriting. This is the idempotent law. Then De Morgan's law, x plus y inverse, then x inverse plus z. Then they apply the distributive law. Then they apply the commutative and distributive laws. Then inverse. Then idempotent law again. Then distributive. Okay. Then inverse. Then idempotent law. Then they solve. So from this function we got x z. So you have to, based on these, how many law we read? 1 2 3 4 5 6 7 8 9 10. So you have to remember these 10. Then you have to apply that which law is applicable for which line for simplifying the Boolean function. Okay. So clear? I hope at your home you will practice this one again and again, and you will remember the equations, the 10 equations, 10 Boolean identities are there. So you have to always remember the 10 Boolean identities. Now, sometimes it is more economical to build a circuit using the complement of a function and complementing its result than it is to implement the function directly. The De Morgan's law provides an easy way of finding the complements of a Boolean function. So recall the De Morgan's law state. So what was the De Morgan's law? Let us see. The De Morgan's law was for n form x y bar is equal to x bar plus y bar, x plus y bar is equal to x bar into y bar. Okay. So again we have written, so x y bar is equal to x bar plus y bar, x plus y bar is equal to x bar y bar. This was the De Morgan's law in two forms. Okay. So let's see. De Morgan's law can be extended to any number of variables. Replace each variable by its complement and change all ends to ones and all odds to ends. Thus we find the complement of. So now we are going to find out the complement. So our function is f x y z equal to x y plus x bar z plus y z bar. Now we are going to find out complement. So this is the complement sign. If you want to find out complement, you have to give this sign. A bar is equal to the bar of whole function. So it will be simplified like that. So if we apply, so what will be the equation? What is the De Morgan's equation for war form? Everyone, can you remember? Hello?
Yes,
Are you
ma'am.
listening or sleeping?
Listening, ma'am.
Are you listening or sleeping? Listening.
Yes, ma'am.
Okay, so what was the word form? Word form was that like x plus
X plus
y,
y whole bar.
then bar. So we can write bar like this way also. Okay. So then the equation was
X
x
bar y bar.
bar plus y bars. Okay. So now, so if we think this is x and this is y, this whole thing is x and y. So that will be x bar, this will be y bar, then this will be z bar. Okay, so x, y, z. So like this way, so we have written. So now x, y bar, x inverse z bar, y, z inverse bar. Now you apply the AND form. So what was the AND form? Can you remember AND form? The AND form was x, y inverse is equal to, what was the AND form? X inverse plus y inverse. This was, is not it? This is the AND form. So apply x inverse plus y inverse. So inverse. Here previously has another inverse. So x inverse. So this will be x plus z inverse. Y inverse plus z. So did you understand these 4 lines?
Yes, ma'am.
Everyone,
Yes, ma'am.
so have to find out the complement of the function. So now I'll go for the next. Through our exercise in simplifying Boolean expressions, we see that there are numerous ways of stating the same Boolean expression. These synonymous forms of logically equivalent expressions have identical truth tables. In order to eliminate as much confusion as possible, designers express Boolean functions in standardized or canonical form. Okay, let's see. There are 2 canonical forms for Boolean expressions. Now we will learn the canonical form: sum of products and product of sum. Sum of products and products of sum. Okay, recall the Boolean product is the AND operation and the Boolean sum is the OR operation. We are recalling this one. In the sum of product and variables are words together. For example, so this is the example of sum of product form. Okay, so these are the product form. Is not x, y. These are the product form. Y, z product form. X, z product form. So all these product form are summed together. This is the sum of product form. Now the product of sum form will be like that: x plus y multiplication, x plus z multiplication, y plus z. This is called product of sum form. Okay, so this is easy to convert a function of sum of product forms using the truth table. We are interested in the values of the variables that make the function true one. Using the truth table, we list the values of the variables that result a true function value. Each group of variables is then worked together. So you will simplify this one at your home: x, z bar plus y. Okay, you will create the truth table.
Okay, ma'am.
Then this one, this slide also, the sum of product. This is the example: product and sum. This is the example of sum of product. Okay. So still this slide is no more today. This is for today's lecture. So now I will upload this slide in our group and I will take your attendance.